The element of computing that's pervasive today is machine learning. And when we talk about machine learning, we often look at the chips and AI accelerators that power it. Now, these systems contain thousands or tens of thousands of chips, not just one. And that's for a reason. The way machine learning has grown, literally only over the past 12 months, has meant that we need to bring massive amounts of compute and memory together to train and run inference on the largest models. Today, that's language. Tomorrow, it could be something else. Nonetheless, there is a drive to enable bigger chips and more chips to talk to each other. One of the key elements here is data movement. And I'm not just talking about chip to chip, but also chip to memory, or host to device, or host to other accelerators. Right now, we're experiencing a Cambrian explosion of how AI is put together, how we train these models, and ultimately how they're going to be inferenced in the future. And if you look at the revenue models of these companies, they're all looking to how they can bring these large models and generate revenue over time through the inference application of this compute. At the heart, I've said, is data movement. As we scale up and scale out these problems, we have to be able to transfer data everywhere. And one of the most important standards today for data movement is PCIe. So if you've never met me before, my name is Dr. Ian Cutress. I am the chief analyst at More Than More, and I run the tech YouTube channel TechTechPotato. Joining me today is Priyank Shukla from Synopsys, who deals with PCIe. So Priyank, welcome, and please introduce yourself.
Thanks, Ian. My name is Priyank Shukla. I am Principal Product Manager of High-Speed SerDes IPs here at Synopsys. It's really nice to talk with you.
So how long have you been involved in high-speed SerDes?
I have been doing this for past 17 years, and I'm really fortunate and privileged to present Synopsys, who have been doing this PCIe technologies for more than 20 years.
Is there anything particular that drew you to high speed? I mean, from my perspective, I'm always thinking about fast things go faster, and that's what makes this industry exciting. What about you?
Right, since the time I graduated, we have seen this data explosion. It was first phase where multiple processors were connecting to each other at higher speed. Now we are talking multiple accelerators connecting to each other. So my career has focused in high speed interconnects all through. So that's what excited me.
So one of the things why I've got Priyank with me here today for this LinkedIn Live, or wherever you just happen to be watching this, is because we are in this very fast moving industry right now as it comes to AI, as it comes to machine learning. But beyond that, there are new ways of compute coming through and accelerators being developed. I think pretty much every major CEO has said this is an amazing time to be in silicon. Whether you think it's the end of Moore's Law and this is next, or whether it's Moore's Law Plus, or Priyank, how are you seeing some of the industry changes in your role, and what needs to happen to enable the future?
That's a great question. Artificial intelligence is the software experience that user gets. To propel next generation of artificial intelligence, you need machine learning or the models that gets trained on large amount of data. So it's called machine learning with unstructured data. So whenever people are interested in AI, they are fueling the next generation of semiconductor or hardware design, which will enable that machine learning at the next stage or next level of data complexity. So whenever people are excited about artificial intelligence, to me, it means next generation of interconnects and faster speeds.
So bigger chips, more memory, more electrons going zoom, 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 zoom everywhere.
And multiple accelerators talking together faster.
And perhaps in a very heterogeneous way, not just a homogeneous way. I think that becomes a very important part of where this industry is going. So right now, when we're looking at accelerators, we've got big GPU. Most of the talk is about GPUs, but then also dedicated accelerators, perhaps with HBM, perhaps with GDDR, or even standard DDR, right? Why are we seeing such a wide array of different compute structures and styles?
Right. So we need to process data through a processing chip. And whenever we process, we need to store that data in a memory. So think about a large set of data that needs to be stored in a chip. And then when it gets processed, stored in memory. So we need the whole signal chain or whole data path, which can be wider and faster. So that's why we have next generation of memories, which are HBM, which is on chip or on die, and then DDR, which goes in the same rack unit, but they're not on the same package. So that's the memory side of the equation. But then you need multiple chips. As you mentioned, GPUs or a different kind of accelerator. Those chips needs to talk with each other in a faster rate. And that's where these technologies, PCIe that we are talking and announcing this month, come into play. So PCIe is de facto standard for chip-to-chip interconnect. And that's what makes it most exciting, that faster this data paths can go, larger the data set we can train on and provide next generation of artificial intelligence experience to users.
So this is exciting because for as long as you've been in high-speed SerDes, I've been playing with PCIe connectivity and connected devices, and perhaps at a time where I didn't realize it was called SerDes. But just to go a little bit into the history, we went from PCIe standards, let's just take that for now, PCIe 1, 2, and then we had this long period of PCIe 3. Right? And the whole goal of gen-on-gen improvements was either doubling speed, either bit rate or transmission or encoding. Why did we have such a long period of PCIe 3?
Right, so PCIe is an interconnect technology that provides a way to provide next generation compute. So when industry was digesting PCIe 3, the type of compute challenges it were facing were good enough for PCIe Gen 3. But in 2012, this was this AlexNet movement where accelerators started to train, and people understood that if we can connect multiple accelerators together with a bigger fibe, you can do more and more. First, it was image recognition, then it became voice, and then large language models came about, then multimodal training. So the application space keeps on evolving. So there's this insatiable demand from the industry, and that's what PCIe across generation is serving.
And the fact that we've gone from you say that's great because we've gone from PCIe 3 to PCIe 4. That was that long transition. Then 4, 5, 6, and today we're talking about PCIe 7.
That's right.
That's been on. It's the cadence has reduced significantly, and it's all because of machine learning, pretty much.
Absolutely.
But we're also seeing the change in the standards. This encoding scheme, we're moving from what used to be a 10/8 bit to the 128, 130 to this now flit structure.
Correct.
In terms of the signaling, we've gone from NRZ to PAM4. It almost sounds like magic if you were to talk about this 17 years ago, right?
Correct. Absolutely. So it just goes on to show the ingenuity of all the engineer and the whole ecosystem. When you place a problem, people will come up with a solution. The way PCI-SIG, the whole industry has come together to solve. You rightly said FLIT was a novel concept with PCIe Gen 6 flow control unit, which included this forward error correction in PCI technology, which nobody imagined. And with PCIe Gen 7, the same FLIT structure is going to transition. So the industry is in fact more comfortable now taking that change. So from 6 to 7, the changes are more or less well understood.
I think from my perspective, I can feel that the PCI-SIG, the standards body behind it, but also the companies that are involved, are more open to discussing the new technologies because it's a more frequent, rapid update. And I think if you don't speak about them, then perhaps somebody else might get in. So are you having more of those conversations with people like me these days?
Absolutely. I would say it takes the whole village to train an AI model. So we need the whole ecosystem.
We're going to run out of villages soon.
Villages, that's correct. So the whole ecosystem, right? When we talk about machine learning and AI, we mainly talk about processor or accelerator. But as you said in your intro, that there are retimers in this rack units. So all these chips get into a printed circuit board that makes a rack unit. And you have accelerator, you have processor, then you have retimer, then you need memory, as you highlighted. Then there are network interface card, because the industry is not satisfied with just rack unit. You have to connect multiple rack units together and you have to scale out. So for that, you need network interface card. That process also needs PCIe. Then there are data processing units. Then there are PCIe switches. So the whole ecosystem needs a silicon-proven solution. And that's where PCI-SIG comes in, so that whenever this ecosystem takes shape, everybody is coming up with their best innovation. And the interconnection between chips is taken care by PCIe. And everybody now talking about the whole ecosystem. That makes it most exciting.
So it's great that you've said a village, because right now we're kind of PCIe isn't the only game in town, and we have to acknowledge that there are others that exist. But most of those are proprietary, whereas PCIe, it's a much more of a collaborative model. What are the benefits of having that collaborative model compared to relying on one single source to provide all the innovation in that stack?
As you rightly said, it spurs the innovation, because if you're committed to an open standard, you have the whole ecosystem coming up with their best innovative technologies. So retimers can come up with the best flight management or fleet management features. Switches can come up with different ways of reducing cut-through latency or caching the structure. So open ecosystem spurs the innovation. And also everybody gets access to a field-proven IP. And at the same time, when the next generation of technology gets deployed, people are not debugging the connectivity-related issue. Everybody leverages the same silicon-proven solution, and people have differentiated offering at the time they really wanted to enable next generation of compute.
I think that's really important to emphasize, because you may think, how can there be innovation in a standard?
Sure.
But it's all about control, it's all about power consumption, it's all about management, and I think you laid that out quite well. Do you find that the more generations that go through this, there are more ideas coming to the table? And Synopsys, for example, is on the board, for the PCIe standards. How has that evolved over time as well?
Right, so PCI-SIG is a great democratic institution where the whole ecosystem comes together and first sets the goal that this is the data rate we have to achieve at this time frame. And then people come up with the ideas that this is how the channels are going to look at that time, because everybody is innovating. So when we talk about channels, what we mean in a PCB, what will be the loss? And those companies that make PCB are also innovating. So they come to the PCI-SIG and tell the SIG that after 2 years, the channel losses will be this. So maybe you should have a standard that complies to that losses. So the whole ecosystem sitting together at a place and standardizing makes sure that you do the real optimization of the system. It's not just the new innovation, but it's a system level optimization, because industry is concerned about the whole data center power. It's not just power dissipated on one chip or maybe accelerator. It's the whole rack unit power. And because it's an open standard and everybody comes together for the next generation, the industry makes really good optimization decisions that ensures the power is curtailed. One thing I really wanted to bring out here is the way PCIe has evolved over generations. When we started, PCIe was within the box or within the rack unit, where PCIe was driving just printed circuit boards. And as I can show you here, we have this example.
I've been eyeing this for a while since we sat down.
It's an ESD sensitive, so you have to probably touch from here. Yeah, that's
Yeah.
correct. So this shows a printed circuit boards, which resembles a rack unit, which you will find with a processor. So PCIe has been traditionally deployed in this kind of printed circuit boards. So here between the chips, you will have a PCIe channel. But as the demand of bandwidth increased, one rack unit cluster is not enough. So what happened is PCIe started going from one rack unit to another through this direct attached copper. So from one rack unit, I'll take it back.
Oh, yeah. So we're handling the expensive stuff now.
Right, so this is direct attached copper or DAC.
DAC.
So whenever you have to connect two PCB rack units, you will use this. So this shows 1 meter DAC, and I have another one which is 2.5 or 3 meter DAC. So now you can connect multiple chips using this copper cable. So
There's the thing here that says 800 gig.
right, it can go up to that.
So super speed.
Correct. So those are the cables that are available today in the industry. So now the whole ecosystem is coming up this way of connecting multiple processor or accelerator together. So this is what PCIe Gen 6 did. But Gen 7 needs even pushing the envelope even further. So now you're going to see PCIe riding over optical channel.
So what we saw before was purely electrical, purely copper. This is the next stage, and I think everybody's kind of agreed light is faster than electrons.
That's true. But technically that's not true.
At
we're
least
the same.
you can get more light over the same area.
On the same channel, correct. That's the right statement to make.
Yeah.
So here it's a very low loss channel, right? Optical. So the power you dissipate is on conversion. But once you're in optical domain, you spend very little power. So that's where PCIe Gen 7 is going. And as we have been demonstrating with our PCIe Gen 7 solution, the physical layer phi can drive this optical channel, multi-mode fiber or single mode fibers. So that's to answer your question, how the whole PCI ecosystem is enabling next generation. So we talked about innovation in the channels as well.
I've been working recently with a number of companies dealing in photonics. And so this is, outside of the chip, but still board-to-board, system-to-system.
Correct.
And the future is that we're going to see directly attached integrated photonics into the chip. So you don't, in the same way that you have like an all-to-all GPU connection today over PCIe electrically, that may be copper, and people are talking about, 512 radix and beyond. It's insane. I mean, if I remember correctly, certain standards 20 years ago they thought wouldn't go beyond 1 gig, let alone reaching 800. So
you're not that old, Ian, are you?
It's so. Let's step back a bit, because the whole point about having a standard is that everybody comes together. And you mentioned it's a democratic institution. There are sometimes some issues with that. Too many people, too many voices, too many interests and financial interests. And so as a result, I know that I've reported on this before. We get this sort of staggered release of the specifications, the different versions, almost like a software alpha beta, but in this case it's 0.1, 0.3. And as we're doing this video now, the key number here is 0.5. Why is 0.5 important to you?
That's a great question. And that's where PCI-SIG has done an incredible job. Whenever they come up with a specification, they follow a predictable path. They announce with 0.1, then there's 0.3 version of specification, and then there's 0.5, where a significant portion of spec, which we call base specification or base spec, gets defined. And conventionally, if you see, Synopsys has been doing this for last 20 years. Whenever PCI-SIG spec reaches 0.5, we announce the whole solution, which is the physical layer, controller, security model, and verification IP. And this is important because at this time, we know the kind of channels this technology has to drive. We know the kind of encoding this technology will incorporate. We know the kind of encryption algorithms which would be needed. So that's why we closely monitor this 0.5, and PCI Gen 7 is no difference. Now we are expecting 0.7 to come out, and then 0.9 and 1.0, which is expected by second half of next year. And that's why the 0.5 is important, that our customer or the ecosystem provider can start adopting our solution so that their product hits the market when the spec reaches 1.0. So we have been doing this for 7 generations.
I mean, I think it's important to realize that chip design takes years. It's not, even though we're in this fast-paced machine learning environment, we keep hearing about new models every 3 to 6 months, and everybody wants a jump in the performance level, 10x, 100x, whatever. But in order to build a chip, it takes 2 to 3 years, even with skilled people.
2 to 3 years is a long time. So foundries have 9 to 12 months turnaround time.
Yes.
So we are talking about 12 months turnaround time. So if you start designing now, and what we call is tape out, meaning giving your designs, because earlier they used to give the tapes to the foundry, right? So that's why it's called tape out. So if you tape out your design today, it will take about 9 months to get the design back. So that cycle is non-negotiable. That's done by the foundry. So if you want your product to hit the market in the second half of 25, you need to start your design now.
Yes, and I think that's important because, as we're recording this, I've just come from events in Taiwan where everybody's talking about the latest chips that are coming out now or within the next 6 months. all the design of which would have been done 18 months prior.
Absolutely.
So
That's right.
So a customer approaches you and says, "Give me some 0.5 IP." You've mentioned you provide the end-to-end solution. Can you go through into detail, what those individual parts are?
That's a great question, and I really appreciate talking with the wider audience about it because people expect the solution to be available like this.
Yes.
So we talked about the 9 months of the cycle time with the foundry or the fab. But there's a lot to integrated design. As you rightly said, Synopsys provides the physical layer and the controller. This is the layer 1 and layer 2 if you compare it with OSI 7-layer protocol. On top of that, we provide encrypted data encryption and verification IP. So all this are RTL logic, register transfer level. So those needs to be integrated with the customer SOC logic. Then you have to run the whole simulation verification through that, and then you have to do tape out. So if our customers are taping out by end of this year, they are starting to integrate the RTL at this time. So they will do the verification. So verification IP is made available at the very beginning, and that's what we have announced. And then we are providing design views for the physical layer and controller so that customers can start adding their logic with this physical layer. And then they are planning to tape out by end of this year, first quarter of next year. So that's what we mean, that we are making solution available so that customers can target their tape out and make their product available when the spec reaches 1.0.
What differences end up between a 0.5 and say a 0.9 or 1.0? Because even if you have a customer doing all that validation, verification, simulation today, if there's a major change, maybe there was no point in doing it in the first place. So how does that tie together with how the spec is built together?
That's where our experience working across generations with this technology comes handy. So when we design this IP, we know the broad brush strokes which are written in stone now, and we have an idea where it's going to end. We have our team, we have 50 plus engineers working with the standard development. So we know the direction the standard is inching towards. So there are a few finer specs, for example, effective return loss. So that's not decided today, but we have an idea because we have worked in this technology over generation where that would land. So this was with respect to the physical layer. With respect to controller, we know the broad brush strokes at this time. We know the data rate. We know the pipelines at this time. So we are adding feature constantly. And we provide this in a staggered delivery manner so that if at all spec changes, customers can incorporate those in their design. So that's why it's important to get started now and being in a close contact with our ecosystem partners so that they can take in the changes that they really want.
When we talk about these standards, especially as they're brand new, in my mind, we're talking about leading edge clients, right? The ones that are wanting to bring a chip out as fast as possible on the most leading edge possible, which must mean that the client base for this initially, is in the dozens, but ultimately maybe in the hundreds. How do you deal with those relationships of people who want it today and people who are showing interest perhaps for further down the line?
So the whole ecosystem has a set of requests. The PCI ecosystem starts from processor and accelerator, goes through retimer, NIC, and SSDs. So we have been with those customers as they moved across generations. So our design teams are knee-deep into their design challenges. So we understand SSD vendor moving from Gen 6 to Gen 7 would expect these features. So we have a set of design leads who are engaged in that specific portion of spec. So they engage with that customer. So that's where our scale from Synopsys comes in handy, that we are enabling whole ecosystem and we have different design teams which are focusing on features which is needed for all these key customers, and they take those customers across generation.
Do you get customers who ask for secret sauce?
Absolutely. So we have to be very careful that it's our technology and your innovation.
Right.
So we have some basic IP intellectual property, and then our design teams work with customers to give them the knobs they need to create the system level differentiation.
Normally, PCIe has been its own thing for a long time, but now we're seeing the evolution of other protocols on top of PCIe, like CXL, and some of the more sort of memory standards that CXL consortium have adopted. Does that factor much into the design of where you sit?
It does. And the great part here is all these standards have made notice of the fact that defining a physical layer, or the PHY, which goes through this 9-month cycle through fab, is really challenging. So the standards you were highlighting all leverage the physical layer from PCIe. CXL doesn't define a physical layer which is separate from PCIe PHY. So the work we are doing with PCIe Gen 7 will enable the work for the next generation of CXL. So the announcement we are making, the silicon proof points we are demonstrating will not only enable the PCI ecosystem, but the other protocol that leverage the same physical layer.
So just to wrap everything around here, I think everybody knows what PCIe is at this point, at least everybody who should be watching this. What is PCIe 7 bringing to the table at the end of the day that perhaps PCIe 6 isn't, and what needs to be built on for the future?
That's a great question. So PCIe 7, to begin with, doubles the bandwidth. And once it doubles the bandwidth, you can connect 2 chips at a faster data rate so that you can do data processing faster and then train models which are more complex and provide better artificial intelligence experience. So that's the problem PCIe 7 solves. Also, because we have leveraged our silicon experience from the last 6th generation, we have provided power efficiency improvement with this next generation of PCIe technology. So up to 50% of power can be saved by adopting this technology. And that addresses the thermal runaway problem that data centers are talking. That in next 5 years, the data center power is going to go up by 80%. That's the projection. So Gen 7 will solve this problem as well, because it's more power efficient and the ecosystem is going to adopt optics, as we talked about, that will save power even further. So PCIe 7 will solve that problem. And third is IDE modules. So there is confidential compute architecture that's going to be implemented with PCIe Gen 7 solution. That will offer a lot of implementer a way of providing cloud training which will be zero trust based security solution. So those are the very high level solution that PCIe Gen 7 offers, which were not there with Gen 6.
What does that mean at the end of the day for people like me or perhaps my grandmother?
So that would mean that AI models can be more complex. So the experiences this artificial intelligence software will provide you will be even more differentiated.
So you heard it here, PCIe 7 enables better machine learning models.
That's great.
Awesome. Thank you for your time, Priyank. Pleasure.
It's really nice talking with you, Ian.